Hi, everyone, and welcome to the USC Viterbi School of Engineering Faculty Roundtable session. This faculty roundtable session is here with our Mork Family Department of Chemical Engineering and Material Science faculty. My name is Paul Ledesma. I'm the Executive Director of Undergraduate Admission for the USC Viterbi School of Engineering. You won't be hearing a lot from me today. I'm just here to moderate the discussion, and what's most important is that you get to know our faculty. We have two of the faculty on the line right now. We have another one on her way in, having some technical difficulties, but when she comes in, she will introduce herself. But before we get to her, and as she gets in, we'll have our two faculty introduce themselves. Why don't we start with you, Professor Zeno?
Hey, welcome. I'm Professor Wade Zeno. I'm an assistant professor of chemical engineering here in the Mork Family Department of Engineering within the Viterbi School of Engineering at USC. I've been here for a little over 3 years now. I'm really liking it here at USC. I teach undergraduate courses in chemical engineering, so you'll definitely see me around if you decide to come to USC. And I also run a research laboratory here where we basically figure out how to understand and re-engineer biological systems.
All right. Thank you very much. Professor Malmstadt.
My name is Noah Malmstadt. I am a professor in and associate chair of the Mork Family Department. I've been here at USC since 2007, so a while now. My research interests involve like things at the interfaces of other things. We do a lot of work with microfluidics, with manufacturing microfluidics. We do some work with biointerfaces and with both production of and analysis of interfacial biological molecule type things like lipid nanoparticle vaccines, that sort of stuff. I also teach undergraduate fluid mechanics. I teach undergraduate polymer science. And I also do a lot of work in curriculum development here in the department.
All right. Thank you very much. And as we said, we have another faculty member who's just having some technical difficulties, but she'll be joining us as well. That's Professor Malancha Gupta. And when she comes in, we'll have her introduce herself as well. But here is how today's session is going to go. We have the hour. We're here for a really tight hour, but we're here to make sure that we get a lot of information across for you in that hour. And so what we're going to do is for the first half of the session, approximately half of the session, not exactly, I'm going to be moderating a discussion of a set of questions that will help you understand more about chemical engineering, the undergraduate program here at USC. And I'll be asking those questions to our faculty. They'll be jumping in. It'll be kind of a roundtable discussion as we go. Towards the latter end of the session, I'm going to open up the Q&A feature. And so for right now, there are no questions from the audience. I just say sit back and relax and listen to everything that's going on. And think about questions that you do want to ask, because when I prompt you to do so, I'm going to open up the Q&A feature, and that's where you're going to type in your questions. You're going to type in the questions into the Q&A feature, and then you all as an audience are going to upvote the questions, and you let us know what are the most important questions to you as an audience that we're going to answer. And we're going to get those questions in that order. So we're not going to necessarily get to everybody's questions today, but we will do our best to get to as many questions as possible. So submitting a question is important, and also more important is to continue to upvote the questions that you want to see answered by pushing them to the top. So just as a reminder, that's what we're going to do. So without further ado, let's get into our questions so you can understand the program. We'll start with a seemingly simple question, but I'm sure it has a complex answer. Oh, wait, we got her. We got it. We're good.
Yes, hold on.
Professor Gupta, how are you?
Good. Hold on. Let me get off the call. Okay, got it. Yes, I'm finally in. Hold on. Technical difficulties, but I'm here.
Okay. That's okay. Well, we have our audience here, and we were just about to go into questions, but why don't you introduce yourself? Your perfect timing. You came on in just the right time.
Okay. Hi, I'm Professor Malancha Gupta. I've been at USC since 2009 as a professor. Before that, I did my PhD in chemical engineering at MIT, my undergrad in chemical engineering from Cooper Union in New York. I'm a native New Yorker. I did a 2-year postdoc after my PhD in Harvard in the chemistry department. And my expertise is in polymer research. So I train PhD students. I've had a lot of undergraduate researchers as well in my lab. And I've taught courses like heat transfer, fluid dynamics, nanotechnology, polymer engineering. So thank you all for joining today to hear more about our department.
All right, great. Thank you so much. I did forget to add one thing. When you get to your questions, folks that are out there, I want to make sure that we're not asking any admission questions or USC application questions. This is not an admission session. We have plenty of those admission sessions that are going on weekly. And Lisa, who's also on the call in the background, she'll put a little message into the chat for you all to have a link. So if you ever want to register for one of those, you can feel free to do so. But today we're going to talk all about chemical engineering in the undergraduate program. So my first question, a seemingly simple question, but likely complex in its answer. We want to see a little bit more about this program. So what the heck is chemical engineering? I guess that's the first question. What is it? How do we understand it? And then I think just to add some context to that, I'm a high school student. I've taken chemistry and I don't know what chemical engineering is. Can you help me understand what this discipline's all about? Noah, do you want to take a stab at this first and then maybe others can jump in?
Well, sure. I mean, I would honestly say that my understanding of the discipline has changed over the years. I would say that at the core of chemical engineering as a discipline is the design of processes. The design of methods to transform matter from one thing to another. Right? That's fundamentally what chemistry is. But chemical engineering combines those ideas of chemistry, right? The underlying physical laws that show how one molecule can be changed to another molecule, with all of the complexity of designing a process. So just moving stuff from one place to another, controlling temperature, controlling pressure, making things reproducible and practical and reliable over time. Chemical engineering as a discipline then goes far beyond just working with chemistry. I mean, it goes to cover all of the concepts of designing reliable processes at all sorts of different scales. So that's where my current understanding sits. I don't know about the rest of you.
Other thoughts?
I'd agree with that. Like I go on to say, like it's the most interdisciplinary branch of engineering, in my opinion, in terms of it utilizes everything else that all the other engineers use. We use chemistry, we use physics, we use math, biology to study these systems and, as I said, transform matter from one to another. And I guess there's a bit of economics in there as well, because you want to do these processes efficiently.
Yeah, I agree with what Noah and Wade have said. Basically, we're applied chemistry and thinking about how to take the concepts you would learn in, say, like AP chemistry and apply that towards practical applications. So a lot of our undergraduates go on to work in very different fields. Like you could think about working at, even like food places like General Mills. You could work at Procter & Gamble, working on like soap and hygiene. You could work in the vitamin industry. You could work in medical industry, because basically what you're learning fundamentally is how to apply chemistry knowledge into different application areas. So I do think that coming into our discipline, you can learn a lot of things that you could apply into chemical engineering, but also into the biomedical field, into environmental engineering. For example, you'll learn a lot of fundamentals that you could apply to energy and environmental applications. So it's very broad what you can do with our discipline.
Speaking of that breadth, I think, Noah, I'm going to have you kind of take the first stab at this one as well. But given that those are the broad ideas of the discipline, how can we explain what the undergraduate curriculum looks like? And given that the idea of studying chemical engineering has some different disciplines that are alluded to in this conversation so far, what can students expect in the types of what are the areas that we're going to go into? Let's start there. What are the areas that exist, the specializations, the emphases? And then if anyone wants to jump in with classes that you teach and maybe help understand what those classes actually are, that might be, I'm setting you up for like a lot of answers. So this is my chance to chime in, but Noah?
Yeah, so there are a few ways to answer that question. And I guess I'll start with the highest level. Mm-hmm. And that has to do with the degree emphases that we make available. Now, of course, you can get a degree in chemical engineering and it's just chemical engineering, and that's great. It's a flexible, broad degree. But we also have 4 specialties available, and that is chemical engineering with biological and pharmaceutical engineering specialty, with materials engineering, with energy and sustainability, and then finally a petrochemical engineering and subsurface science specialization. So we can speak to all of those. So when we talk about biological and pharmaceutical engineering, that's leaning towards the design of processes for manufacturing drugs and formulating drugs and making natural products. So things involving bioreactors, which can go all the way from fermentation processes to advanced next generation metabolic engineering to produce high value drug molecules from biological reactors. And we've got materials engineering, so that's very broad. It covers everything from functional materials like electronics and solar cells to structural materials like composites, polymeric materials, and applications of all of these, including emerging approaches applying machine learning and artificial intelligence to materials design. When we talk about energy and sustainability, that really goes to one of the core competencies of chemical engineers. And I talked about process design, and Malancha talked a little bit about economics. So one of the real directions that the field is evolving is this idea of life cycle analysis to understand the total fate of some chemical feedstock or some chemical some chemical that's going into your process, and designing the process for sustainability so that you're not sending things to a waste stream, but you're constantly figuring out new ways to reuse that. So when we talk about sustainability from a chemical engineering point of view, one of the terms we use is circularization. So instead of having something going in, something going out, you try to loop all around and minimize the waste of any given process. That's actually kind of a huge emerging theme in the field. And then when we talk about the subsurface engineering, this also fits into a lot of sustainability goals, because in addition to petroleum production, the things that subsurface engineers can do include geothermal generation, carbon sequestration, understanding the behavior of water tables. So all that stuff. All right, so that I guess that speaks to the degree emphasis options that we have right now.
That's great. And then Wade or Malancha, do you want to jump in with the undergraduate classes that you teach and maybe kind of dive in a little bit into those specifics of what that class is like? I mean, just to give again some more context, what is the college class like considering you've only taken high school? And then what do these words actually mean? What does that mean you do, if that makes sense?
Yeah. So maybe I could speak to a little bit about like the fluid dynamics and heat transfer types of courses that are like, basically it's like in high school, you're doing differential equations, and then you come in and you take a series of courses about fluid and heat and mass, and where it's similar to what you were doing in calculus, but with more realistic applications. So for example, like going back to like biomedical applications, I know in heat transfer, we would give problems where it's like, you want to like use cryogenics to like freeze a tumor. So you have like certain temperature boundary conditions. So you're thinking about your calculus, examples, but giving it a more realistic application in the class. And back to thinking about learning your core concepts in chemical engineering and applying it out elsewhere, like in fluid dynamics, we'll learn about Navier-Stokes equation, so fluid flow through a pipe. But for, some applications, that pipe might be a reactor that you're using to make a certain material, but it could also be a vein in your body, or like something where you're applying it to something large scale for some application, or you're making a mini reactor that's more biological, or you're trying to mimic something in the human body. So you're using similar equations for each, but you're changing the boundary conditions, and that's how or like the assumptions in your model, and you'll learn that in the undergraduate classes. And then, Noah spoke to some degree about the emphases. So like, in addition to the course that we all teach, we teach, electives, like, for example, like polymers, where you could come in and then that's more project based the way I teach it. So you could say, like, I'm interested in polymers, like those you use to make Legos, for example. But there might be a student who says, well, I'm more interested in sustainable, biorenewable materials, like different kinds of polymers that are naturally found. So you can like kind of tailor it to your interest as well, so that you're still learning the fundamentals of polymers, but you could apply it to like whether you want a medical application or a sustainability or an energy application. So that's what you would do in the everyday classes. And now I'll let Wade chime in for what he thinks.
Yeah, I mean, Malancha did an excellent job of covering like type materials. So the classes she described specifically are generally upper division courses you'll take during your junior and maybe your senior year. And again, like the same type of mathematical framework can describe multiple systems. So how heat moves from one place to another, or how a molecule moves from one place to another. It's just the application that you're using for these equations. In your first 2 years, a lot of you will take maybe a lot of like introductory courses or courses to general courses. Like I teach a sophomore level class in numerical methods and computer programming. So in that class, I basically teach students how to program. So for those of you that don't have programming experience, you'll learn how to program specifically in MATLAB, but that programming language can be applied to a lot of different other programming languages such as Python and whatnot. The same kind of logic applies for all these different computer programming, and you'll learn how to solve different types of problems in chemical engineering contexts. And then after you kind of take these introductory courses, I believe you also take a course in basically like heat and energy balances. Then you take a class in separation processes. Then once you take these kind of core introductory chemical engineering classes, then your junior and senior, that's when you take these transport classes that we were talking about with momentum, heat and energy, as well as classes in kinetics, and then eventually classes in reactor design and things like that.
Great, thank you so much. Now, can we shift gears a little bit? And that's a great detail on the curriculum and classes. But can we talk about the other side of academia, which is research? Can we talk about what research is going on in your department, and if any of you even want to dive into the things that you're doing research on in particular?
I'll start then. I work on polymers, so I work on making thin polymer films. So for those of you listening, the analogy I give to people are like Teflon-like coatings, so non-stick coatings or hydrophilic coatings. Like you could think about contact lenses, so water absorbing or water repelling coatings. The novelty of our lab is that we use gases to make these coatings, and we've had several undergraduate researchers in our lab over the years. So we've had undergraduate researchers who come in and they work undergraduate student. Like, for example, the graduate student has a big project that they've been working on for many years, and like the undergraduate might help them with doing scanning electron microscopy or doing some other analysis as part of the project. I have lots of undergrads who've become authors on these papers by contributing a small part to a bigger project. But I've also had undergrads who come in and do their own projects. So for example, I had a student many years ago where we were trying to do a more sustainable, environmentally friendly nail polish, which is actually quite challenging. There's a reason there's so many compounds in makeup. So, we had come up with this project, and she was independently doing that. I have some undergrads right now trying to use a cotton candy machine actually to do some interesting polymer science as well. I will take undergraduate researchers in either forms, right? Either you want to assist a graduate student on a bigger part of the project. For example, we have a undergrad recently who was on a paper who he did a lot of the computational work for a graduate student who was doing the experimental work. And we have another undergrad who's been doing some contact angle goniometry for another student's project. And so there's that, or you could come up to me with like, hey, I've got some idea, like I'm really interested in sustainability or medical field, like these are the areas, can we like devise an independent project? So I've done both. I'll let these guys answer now.
Well, before we do that, now I'm so curious. What are they doing with the cotton candy machine? That is it food or what's happening?
Well, there's okay, so it's been done before. So we're not the first to do this, but you could do one of two things. Actually, we're meeting this week to decide which to do. So you could either put a polymer solution in and try to like get the fibers out of it, or you can make sugar, which is what cotton candy is, so spin sugar, and then use that as a mold, essentially like a template to deposit your polymer on, and then you dissolve the sugar that's inside, and you can make these kind of like, we go back to biology, you can make these kind of like capillaries, right, that mimic the human body. So you know, in the last decade, people have done this kind of stuff before, so we're trying to explore what we can do, because then it could be something that the undergraduates can do by themselves, you know, kind of lead the way.
Yeah, now I'm just going to be very suspect of any type of carnival event that happens out there on the plaza when you guys are hosting it. If there's cotton candy, I don't really know if I want it now. Is really
no, there's safety first. So all lab equipment is has to be, as Noah and Wade know, labeled for lab use only.
Okay.
Right,
great.
Noah? Right, Wade?
Exactly.
Yeah, we use aluminum foil in the lab.
Aluminum foil.
And you have to label it for lab use
for lab
only.
use only.
Okay.
We have a microwave in my lab.
Don't
say not for food, and
Not
that
for
one.
food.
Not for food. Are you
Yeah.
using that for experiments, Wade?
Yeah, just if we're lazy, you want to heat up some water in the microwave. So
There you go,
waiting on
but
a hot
it's for
plate.
lab use.
Yes.
For lab use only. Exactly. Not for coffee.
Exactly.
Wade, do you want to jump in with your research?
Yeah, so I would say in general, we have kind of 5 research thrusts for the department that aren't necessarily, they're not mutually exclusive, but like we have one thrust in sustainable and renewable energy, another thrust in improving health and wellness, which is where my research mostly falls. We have a emphasis in data science and machine learning, another one in quantum materials, and another one in advanced manufacturing methods and materials. So with respect to what I do, which is under the health and wellness category, my lab basically aims to understand and, I said, engineer biological systems, which in itself is kind of a broad definition, but we aim to study the molecules that make up your cell and figure out exactly how they do the things they do, and maybe ways downstream for making new therapeutic intervention and things like that. So we have a heavy emphasis on proteins that are involved in neurodegeneration. So right now we have a big research thrust looking at the main protein that's involved in Parkinson's disease and understanding how that functions and how it basically gives the onset of what you see in Parkinson's disease, which are these protein aggregates that form in your neurons and disrupt neurotransmission. We have other projects where we basically take biomimetic particles, so particles that naturally exist in your body, such as particles that transport cholesterol around, and see if we can engineer them to deliver other things and cross your cell membranes as well. So that's just to kind of give a flavor of the kind of things we have going on in my lab. And the kind of tools we use things like optical microscopy with high resolution, and we use like fluorescent tagging so we can see these molecules on very small length scales, so down to a few hundred nanometers, so a fraction of how thick your hair is. We can get that kind of resolution on some of the things we image in this lab.
So you're here to make sure that I can live longer, is what you're saying?
Yes, I'm trying my best.
No, anything else you want to add on to that?
Just want to give a really quick overview of the kind of researchers we have in the department. So we actually, on the undergraduate level, we offer chemical engineering degrees. On the graduate level, we also offer degrees in material science and petroleum and subsurface engineering. So it's actually a very broad department. I would sum it up by saying that these are the people in the School of Engineering who work most closely with matter and the structure of matter and making substances, whether they be chemicals or materials or energy and energy substances. And there's just a tremendous amount of research variety spanning these disciplines within the department.
Great, thank you so much. And I also appreciate the ability to get such complex topics summarized into such things. Gabby, I'm lowering your hand. We're not taking questions right now. If you weren't here in the beginning, we will be taking questions through the Q&A process in a minute, so we're not using the raise your hand function today. But thank you for jumping in. We will have a Q&A section in just a little bit. My next question for all of you, because I just lost my set of questions. Oh, I know what it is. Where does this all lead for our undergraduates? And this is not necessarily a data approach question, much more anecdotal, but where do our students go after graduation? What types of companies do they end up working at? People go to work, people go to grad school. What happens to them? What can these students expect for their future? No, you want to start us off?
Yeah, so in terms of the kind of industries people are going into, I just talked to someone who's trying to choose between a job in the cosmetics industry and a job in specialty materials fabrication. So that just gives you an idea of the kind of choices that people have, right? He's choosing between a job in L'Oreal and a job at a company that I've never heard. That's a tiny startup that's coming up with new methodologies for making very specific materials. So more broadly speaking, we send a lot of people into the microelectronics industry. So this is manufacturing electronics rather than designing electronics. We send a lot of people into the production end of biotech and biopharmaceuticals. We send some people into the classic traditional big chemical industries. So things like DuPont and the other big chemistry, 3M, that kind of stuff. Probably like 5 or 6 people each year into PhD programs in grad school, but then a couple other people going in medical school, people going to consulting. And then more and more people are interested in environmental and sustainability type applications. So people working on things like water or things like remediation of environmental pollution. Do you two want to add anything further?
Yeah, any other companies you all know of as well?
I mean, I just want to add that we also have students who join PhD programs or leave our program for a master's or PhD program or an MBA type of, like an advanced degree as well. I think that's a decent sized group. And I think I wanted to add something maybe it was to another question, but also even if you major in our department, you could always do research in another department. I just want to add that we have a lot of students who are majoring in chemical engineering, but they do research for a chemistry professor or a civil and environmental professor. So that's always an option as well. I don't have any extra industries, but basically we've had over our time also students go to I remember a vitamin company, microfluidics company, basically there's so many options. I know my students who are interested in sustainability are now looking into places like Beyond and Impossible that continuously are hiring chemical engineers and other kind of food sustainability types of companies. Wade, do you want to add anything?
You all really covered everything.
Yeah.
The only other instance I can think of, there's one student that went into defense. She went in to be a nuclear engineering program for the Navy. That was another option that wasn't covered. But other than that, yeah.
Right, great. And so for all of you that are itching to answer questions and are not listening to me, you keep raising your hand and putting your hand down. I just opened up the Q&A feature. So at the bottom of your screen, there is a Q&A button in there. Start typing in your questions. Ask as many questions as you like. The more questions you put in there, the better. And then you all can upvote the questions. And so I'm giving you this fair warning. I have one more question that I'm going to ask our faculty panelists. And in that time period, I hope we can fill this up with as many questions as possible. So go down to the Q&A button, type in your questions, and everyone else needs to start upvoting them as much as possible. And keep in mind, some of these questions I bet we already answered. So we'll get into these in just a minute. And so our faculty, let's not worry about the Q&A for just right now. I want to get into this one last question. So the other question I have for you all is the future of chemical engineering as a discipline. What are you excited about what's coming down the road? Where is it going? What do you think is going to be happening with this discipline as we move on here? Whoever would like to start.
I think the main things are sustainability, right? Like it's clear that that's a really big topic that's important, but also that students are interested in. I know that we've been talking a lot about that in the department, trying to meet our courses with the interests of students to figure out what they would like to see. And it's clear that chemical engineers are going to play a huge role in sustainable materials, sustainable energy. I'll let you two add in.
Well, I mean, I think that goes to the core of where the discipline is going, and there's no question about it. Like even my own research has gone radically in that direction over the past 5 years. Right, I've gone from doing like pretty abstract stuff to building chemical reactors for making catalysts for carbon dioxide reduction. And I've started introducing all these optimization tools for reducing the lifetime costs of these catalytic materials, based on like advanced optimization algorithms and machine learning and artificial intelligence. And I've also started studying the biological effects of microplastics. The entire field is leaning in this direction. Nanoplastics, no, microplastics are old and busted. Nanoplastics are the new.
Microplastics are so yesterday.
Yeah, we're doing nanoplastics now.
Wade, anything else?
I mean, I agree that that's where things are heading. I haven't personally delved into any sustainable research yet, but we'll see. My lab's still pretty new, so we'll see where the field sways my lab over the next few
also
years.
Biological applications, Wade, right? Like
Oh,
the
yeah.
last couple of decades, chemical engineering branched into biomedical engineering, right?
That
And
is very
so,
true.
Yeah,
Yeah,
so
like biology traditionally isn't a part of chemical
Right.
engineering. That's something that's really started to become mainstream in chemie over the last like maybe 10,
yeah,
15 years at most. So
Yeah.
yeah, that's still a
right, that will
relatively new
continue on,
growing area.
right? That will
Yeah,
continue on.
which is why I chose it, because at the time when I became a chemie, I've only been a chemie for like 10, 15 years. So like this seemed back when I was this is like the new emerging area. So now it's starting to go through that phase of now it's starting to become an established part of chemie. So I think like sustainability is now kind of in that phase where well, from now it'll become a heavy part of chemie.
I think just to add a comment, that's something that I know you all know very well, and it's interesting to hear you all talk about this as it's been woven into all of your questions. But all of you have added a sense of fluidity, no pun intended, to all of your questions, that things are constantly changing and things are constantly evolving. And it started with, I think, Noah, you started with, here's what I used to do, and here's now what I'm doing now. And I think a lot of high school students come into an area such as chemical engineering or an engineering discipline in general, thinking that there are things that you do. These are the things. So they want to know, what are the things I will do? And some of the answers are, they're going to be in this direction, but they're going to evolve and move and change. And so hopefully people can come in with that sense of an expandable brain that's going to move and adjust with that. And as the future keeps moving, and that's an important concept to have. So I appreciate all of those comments. We're going to dive into our Q&A feature. So as a reminder to all of our audience, you are driving the conversation here. You can keep adding questions as much as you want, and I will constantly remind you over the next 20 minutes or so that you're in charge of upvoting. So don't just upvote it once. Keep going back in. You want to see other things pop up to the top? go down and upvote those questions. We're going to answer the questions in the order that they are at the top. So I will kick us off here and get going with Bo's question. Bo, thank you for your question. He asks, to what extent do projects and research involve work from multiple disciplines, i.e. materials, sustainability, and biomedical, working on microplastics and or reduction thereof? Who wants to take this one?
Well, I can speak to nanoplastics.
Yeah, I was going to say we already shut down microplastics a minute ago.
Well, so my lab is working to understand how nanoplastics, environmental nanoplastic waste, interacts with the cell membrane to disrupt the cell membrane and damage cells. But this is highly collaborative work because my group is good at doing cell membrane type stuff, but we're not really a plastics group. So we've been collaborating with a research group in the chemistry department, Megan Pfeiffer's research group, and they're putting a tremendous amount of effort into building new analytical tools for understanding what exactly is in these environmental plastics. And we've also been working with a government organization, the South Coast Water Quality. I can't remember the full name. It's got a really long acronym. But they've been, so we've been collaborating with these guys. They go to the LA and San Gabriel River and collect environmental samples. And we've been taking those, purifying the nanoplastics out of them, seeing how they interact with our cell membranes, then taking them to Megan's lab, where she figures out exactly what plastics are in there. So there's really this this kind of loop of collaboration across disciplines, right? Environmental science, biophysical science, and chemistry.
Right. Great. Thank you so much. Our next question comes from Gabby, and I can take this one. How many students are in the chemical engineering program, and what is the percentage of men versus women? Gabby, the number changes from year to year, but we, on average, are bringing in around 25 students into the undergraduate chemical engineering program every single year for our first year class. We always bring in also transfer students every single year, somewhere between 5 and 10 transfer students every single year. So they're coming at different points. Percentage of men versus women, I don't have it off the top of my head for the specific department, but last I remember, I think it was roughly 45 to 46% women, 54% men. So we're just right in there in the gender parity range for this particular department. We are gender parity for the last 5 years in the entire school. And that's not because one department is heavily weighted. Actually, almost all of them are in the 45% and up range. So that's exactly a really nice balance that we have there. So Gabby, thank you for your question.
Just from my own anecdotal experience, it's about close to 50% in my classes that I've been teaching the last 3 years.
Great, thank you. I'm glad it's translating in the classrooms. And then maybe that might also help. Well, this is the total number of students coming in. That doesn't mean that's how many students are in your classes, because you all talked about the different emphases. People are taking different tracks. I mean, so your class sizes are very small. Can we talk about that? Your class sizes, Wade?
Sorry. So my classes, the classes I teach are required classes for all chemistry, so it's not specific to different emphases. So those class sizes on average are usually on the order of 40 students. And that's at usually probably 35-ish at the sophomore class, and then maybe 40 or slightly higher at the junior level, but usually in that range on order of 40.
Great. Cool. Great.
And then electives will be closer to 20.
Okay. That's awesome. Afan, I apologize if I'm getting your name incorrect. For someone who is currently stuck between chemical engineering and environmental engineering, I love this question because people love the word sustainable energy engineering. I'm getting that a lot, saying they want to study sustainable engineering. And I always ask, what does that mean? But I think when they look at our programs, they're seeing chemical and environmental kind of somewhere in between. Would they be able to figure that path during my journey getting a degree? Is that something that is done after a chemical engineering degree is obtained? Can we talk about the differences of these programs, or basically, because they're not here, why chemical engineering is better than environmental engineering? And of course, when I'm with environmental engineers, I'll ask them the same question on their side. But how do we address this question for Afan?
So can I speak to something a little broader perspective
Please.
before we get into those details?
Yeah.
And I actually think that this is something where USC is particularly strong because of the progressive degree program. Right. So if you identify if you're interested in pursuing master's work, a master's degree, then it's possible to do your undergraduate work in chemical engineering and study environmental engineering as part of a master's program. So you're not cutting yourself off by choosing one way or another in the undergrad. I will say as a caveat, if you're choosing either one of these engineering disciplines and change your mind in your junior year, there'll be a lot of catching up to do. The engineering degrees ask a lot of students. You all know that already. You know that these are disciplines that have pretty intense curricular requirements. It's a lot of work. So trying to make the change halfway through can be challenging. But the master's degree is always an option if you want to kind of switch from one to another.
Great.
Get exposure on both.
Okay, thank you for that. Appreciate that. Just put a reminder into the chat to all of you out there to keep upvoting because we're running out of people that have voted on some of these questions. So they're all going to start balancing out. So we want to make sure we answer your questions that you want. Dimitri has said, can you talk about the different concentrations within the chemical engineering major? Dimitri, we already did that. Unless you Noah, you think you want to go into some more detail on this?
Well, I think it is a legit question to ask what they entail, like what actually, like boots on the ground. What's the practical difference between these?
Sure.
And so it's basically 16 units, so four 4-unit classes that are tailored to the particular degree emphasis. So everyone takes the same core classes, but what the emphases are a tailored set of 4 classes for each of the 4 emphases taken during your junior and senior years.
Okay, great. Heidi's asking a question. Just a reminder, folks, this is not an admission session, so we're not going to answer admission questions here. If you want to go into admission session, please go to our event. It's in the chat that we have that for that. Heidi, you're asking about, basically, you're trying to calculate your chances of admission. The chance of admission to USC this last year was 8%. This next year, it doesn't matter what happened last year. What happens next year is what's going to be interesting, and it might go down even more than that. So the number of applicants doesn't matter. We adjust our admission rates based on the applicant pool every single year, but just a chance of admission, you should know that. Keon is asking, will students be able to pursue their own individual research projects within the mentorship of a professor? And Malancha, you were speaking about, you basically said yes to this and gave some examples earlier.
Yeah, I think it depends on the professor, but some professors usually have an undergraduate assist a graduate student, get mentored by a graduate student or a postdoc. And then some professors are open to having a student more interested in developing their own project. So it would really, like, if you're interested in developing your own project, you would find a professor who would fit that for you. So most of our undergraduates talk to multiple professors before they usually choose someone to work under anyway.
Thank you so much. Jaden is our next question. And keep upvoting, folks. We're running out of these upvoted questions. Since chemical engineering covers very broad subjects, will upperclassmen be able to choose more focused fields of classes to study, for example, toward bioengineering, mechanical engineering? That's essentially the emphases, which is what we've been talking about, Jaden. So I don't know if there's anything you all want to add to that, but we've kind of answered this question as well.
Well, the only thing I would add is that, you have available to you every course taught in the university.
Right. I want to do this one thing. Will you make a course for me on it? So,
well, but yeah, I mean, so if you don't take if you take just the general chemical engineering degree with no emphasis, you still have those 4 electives. And, you can work with, a faculty advisor and our professional academic advisement staff to figure out which 4 classes meet, whatever your interest is. And, USC is a huge university. There might be things in the chemistry department, the physics department, the environmental engineering department, the biomedical engineering department, all over the place. And you have those 4 classes to customize.
Great, thank you. Susanna is asking, what are the most important fundamental concepts that chemical engineers use?
Well, I think what differentiates, kind of going back to the previous question of mechanical, I think that person asked about mechanical engineering. A lot of our core classes have some similarity to the other engineering disciplines, particularly civil engineering mechanical engineering. So for example, mechanical engineers also do fluid dynamics. The difference is that we have like a chemistry component that gets mixed into the classes. So like in addition to thinking about fluid flow or heat transfer and stuff like that, we have chemistry. So things are reacting, molecules are reacting. So you could think about, I mean, I remember when I was a high school student, and I was also trying to think about all the different disciplines. I was deciding between chemistry and chemical engineering and environmental engineering. Many of the questions are similar right now. The students are trying to figure, and I chose chemical engineering because it would combine my love of chemistry with like what I wanted to be, which was an engineer, and maybe even work on environmental engineering. Then I found that chemical engineering was kind of in between all of that, right? I would be able to do chemistry, but I would also be able to do large scale chemistry, which is applied chemistry, which is chemical engineering. And that chemical engineers do work on problems related to filtration, chemical remediation, and all of those questions that fall into that environmental engineering discipline. And so, for example, all of us on this call have worked on membranes and separations, and we've taught classes like that. And those types of classes are very important for like getting clean water and sustainable application. So that's kind of how I'll answer that question. I don't know if you guys want to add anything in.
It sounds like, simply put, what concepts most fundamental is probably chemistry, right? To differentiate us from most of the other engineering.
To you, Wade, why would someone want to study chemical engineering versus chemistry? Because I like Malancha's take on that, where she was going with that, and I think that's a core question of some of our students. Of, I understand what chemistry is, and you're in a whole other world. So,
right. So I mean, traditionally the difference between chemical engineering and chemistry is application, right? Mm-hmm. So all the concepts in chemistry is important, right? We take all the chemistry classes, so we understand organic chemistry, general chemistry, analytical chemistry, so that we know how to actually apply it. And that's what the difference is between a chemical engineer. How do you actually apply this to a process and use it towards transforming matter in energy.
Okay. It's funny you mentioned organic chemistry, because our next question, and folks keep upvoting because we're running out of the upvoted questions here, is Alex asking, how important is organic chemistry for chemical engineers, and does this depend on their emphasis?
I'd say it's pretty important, and it's particularly important if you go into the biological aspect of chemical engineering, because you really need to have a firm grasp of OChem to understand complex biomolecules and understand their structure.
So from a practical point of view, we require 1 semester.
Yeah, it's in every degree program.
Yeah,
if that's what you're asking. And the second semester of the standard chemistry, organic chemistry, 1-2 series is an option. If that's towards your interests, you can take it as an elective. I mean, it really depends on what you're doing as to how much you use organic chemistry. Yeah, I was just thinking about some polymer stuff, and I really needed to have a pretty strong basic understanding of organic chemistry to understand what was going on with the Malancha. I was actually looking at the stuff that we were doing together and trying to figure out what was going on with those organosilanes, and I think I figured it out.
Yeah, and I think this is back to the other question, but I think like going back to chemists versus chemical engineers, right? Like a chemist might make a little bit of something, right? Like practically speaking, they've come up with the synthesis route and they just like made a small amount. Where are the people who come in and try to scale that up? And for those of you who might have heard us say scale up, it's like, how do we make a process that's economical? Economics has come in. And sustainable. How do we like not use a ton of really bad organic solvents to do this? Like, how do we do this in the safest, economical way to go from the small amount to a large practical amount? So like, for example, one of my friends works on, trying to have like injectable pharmaceuticals, right? So like probably a chemist came up with the pharmaceutical, but she's working on how to put that in a syringe so that it comes out at a certain viscosity and it's scalable for large scale consumption. That's where like really the applications are coming in.
Yeah.
If that gives a example.
I just want to interject real quick. Oh, sorry, just something that might not be obvious to all the students here. Then we talk about scale up. It's not it's not a trivial process. It's like, yeah, we figured out how to make it. So you might just think, okay, just do it bigger. It doesn't work that way. There's a lot of complication steps that go to taking something from the benchtop and making mass production of it.
Yeah, I mean, I always think about consumer products, and I think of the, like the newest iPhone, right? The newest iPhone comes out every single year, and this year they're making a huge deal about titanium. And it's not like titanium's anything new, but the process, the chemical engineering process, the materials engineering process to scale that up for mass production in the phone and the sustainability built into it, that is a huge chemical engineering, material science element. And people don't think of Apple as a chemical engineering company, but they're going to employ chemical engineers down the road. I think a lot of people miss that connection of doing that. Would that be a helpful addition to this conversation as well?
Yeah. That's exactly it, right? Is that a lot of the products that you're using, along the way somewhere, chemical engineers are involved.
Right, exactly. I think that's that's kind of the core of some of these questions, which is like, what will I do? And so I don't know if I want to be a chemical engineer and environmental engineer because I don't know what I want to do. And the idea is like the application of your degree program later on has multiple outputs as well, which a lot of people really freak out. They think they have to choose this degree program from the outside looking in, and that's going to chart their path for the rest of their life. And the idea of an engineering degree program, regardless of discipline, has multiple opportunities. And so I'm always trying to help students understand, like, you're not choosing your end of life here. You're choosing the beginning of questions you will be asking yourself as you go throughout this. Goes back to the fluidity of your guys' brains and the evolution of research and the concepts related to engineering. It's just once you get into it, you're like, oh, I have more questions. You don't know more. You just start asking more questions, which is, I think, is an interesting concept related to it. JD asked about summer internships, and we talked a little bit about end goals as far as like where students go, and they're interning at those same companies. But can we talk about any experiences, maybe anecdotally, of students interning and where they're interning?
So this guy was talking about who had a job offer at L'Oreal, interned there first.
Yeah.
I mean, we've had Amgen interns,
BASF,
Chevron. I don't have a list in front of me.
It's okay. That's
Paul, do you have an answer as to approximately what fraction of Viterbi students wind up doing a summer internship? It's high.
Yeah, well, I think that the number is always questionable on whether a student wanted an internship. So that's the first part too. So I've never known of a student that has ever wanted an internship that did not get it, because we're bringing hundreds and hundreds of employers onto campus to recruit you as undergraduates for internships, co-ops, and then ultimately full-time positions after graduation. And so what's interesting to us, I think, from our end of the spectrum to our audience, is that when we think about jobs, that's a process, right? It's similar to a chemical process. They go in as interns, they start that process, and they come out and they go into those full-time positions afterwards. Those energy corporations, those material corporations, those sustainability corporations, environmental consulting corporations, and then things that are quote unquote non-chemical engineering, but like we talked about consulting, for example. Engineers from all disciplines go into consulting, whether that's technical consulting, things like Accenture, Deloitte, KPMG, all of these things related. They want engineers in there regardless of discipline. So it's kind of an application of that. And students are interning at these companies because that's where they get the experience to then get the job offer. You don't go through this education and then get a job offer. You go through the career planning and services process that we have our own career center here in the engineering school, where we have a full-time staff devoted to creating those relationships and helping you connect with those employers. And internships are not something we offer. It's not part of the curriculum, JD, to your question. It's something that students are doing on their own, and we're helping them. And they usually intern. It's a full-time job over the summer. And students are regularly interning over the summer because that's when you don't have the classes. Our curriculum is a traditional 8 semesters, fall and spring. You do that 4 times. And then students are traditionally doing internships over the summer and working full time, and honestly making good money as a result of that, because they're paid full time. We have time for just one more question, and this comes back to Gabriel's the one with the winning question. So, what types of research do students who choose a concentration in energy and sustainability typically pursue? And I'll add on to this. Your research isn't guided. This is a little bit what Professor Gupta was talking about. It's not guided by your major necessarily. And so it's not like you have things that are chosen for you. Research is not a predetermined path. It has to do with interests that you may have and faculty you reach out to. Just kind of priming the question for you all. Or did I just completely answer it?
No, no, you did answer it. I mean, that's the point, right? So you might have an emphasis in polymers. So you polymers and materials. So your classes, your electives would be in that area. But if you choose to do research, who you would do that with doesn't have to as Paul says, it doesn't have to match your emphasis. So what you would do if you wanted to do research, what most of our undergrads do is they go on our departmental webpage and they look at what we're doing. They get on our web pages. Most of our labs have web pages that explain like our recent papers, like what projects we're working on. And then based on the research, you usually start like reaching out. And we always want people to reach out to lots of professors so you can have some conversations before you choose your lab. But you could also explore like environmental, or as I said, a lot of our students actually do research in the chemistry department as well, right, Noah? Like we've got quite a lot of chemical engineers there. And so if you're doing, I think the question was about petroleum or energy or whatever your emphasis is, you might want to actually match it, right? So let's say you had an emphasis in petroleum, you would look at those professors, maybe you want to do research under them, you would reach out to them. But if you wanted to do research in another area, you could just basically reach out to any of the professors at USC, whoever you want to do research for, and see who matches up to you.
I think that's a fantastic place to end on. And I want to thank our entire audience for joining us tonight. I truly appreciate it. If you missed any part of this, we're going to make this a recording that's available on our YouTube page. So if you just search for Viterbi Admission on YouTube, you'll find that. I'll also send you a follow-up email to give you a link to that a little bit later tonight. But thank you again for joining us. And most importantly, thank you to our faculty who spent time out of their day to come speak with you. So Professor Zeno, Professor Malmstadt, Professor Gupta, I truly appreciate you being here. Thank you so much. And I hope you all will get your applications in by November 1st. We've got about 2 weeks before we get to that deadline. So thank you very much, everybody. Have a great evening. Bye-bye. Fight on.
Thanks, Paul.